look around the room, there's much fewer people than there typically is. Why is that, do you think? Because assignment 1 is due tonight. So for those of you hunkering down, I guess I should be talking to the camera. Good luck. Almost done. Who's submitted? Okay, good job. Big assignment? Good. Well, there's another one coming. This lecture is probably one of the most crucial on the concepts for assignment 2 and therefore your time in this course. So many people do watch this one a bit later after they finish assignment 1. You know, as we know, the pace really ramps up. So for those of you that were able to submit a bit early, congratulations, that's really good. Take it easy and look after yourselves, but you do need to pay attention today. So before we start, we should recap pointers. Feels like a lifetime ago because last week was the midterm break. So let's talk about pointers for a bit. Pointers are a variable data type. That's what they really are. Right? Data types signify to a programming language the amount of memory that should be reserved when you want to create a variable of that type. That's why they exist. They communicate to the computer and to programmers what we're storing in a variable. So if I'm storing an integer called, age, what does that say? It says a few things. It tells programmers the type of information I want to store in that variable, right? And what is that type of information? What do we know about integers? A whole number, in fact, not just a number, right? A whole number, but that's exactly right. It also tells the program, the computer, less so the programmer, although it does tell us this, it tells the computer, okay, well, what do I need to do to store a whole number? And we've reached agreements, okay, this computer on this particular operating system, on this language, is going to store 32-bit integers, right? So 32 zeros and ones will be reserved to store the zeros and ones required. They can store up to about, is it 2 billion? Negative 2 billion to positive 2 billion, right? So it's an agreement of the type of data and how we are going to store it, because the way we store integers, the way we arrange those zeros and ones, we also need to agree on that, yada, yada. Okay, it doesn't really matter. So that's the data type. A pointer, right, is just a different data type. It's nothing else. It's a variable that stores data. Now, what is that data is different, right? What is the data of a pointer? Always. A memory address. That's right. Did you say that? Oh, sorry. I echolocated incorrectly. Good job. It's a memory address. It's always a memory address. And so pointers are a little bit different because they can point to a real data type. So it could be a memory address that points to an integer. It could be a memory address that points to a double. It could be a memory address that points to some struct. It doesn't really matter. But no matter what, at the end of the day, if you've got a pointer, you have a... Someone else? Everyone? You have a memory, yeah, you have a memory address. That's right. Let me shut the door. And the memory address refers to the location in RAM of some other data of that type. Okay, once we have a pointer, we can do a few things with it. So we can follow the address to the real data. That's called dereferencing, and you use the asterisk, right? And we can, well, this isn't what you do to a pointer, but if you've got a normal variable, like an integer, and you use the ampersand in front of it, you can get, the address of that location. And then you could, for example, store that in a pointer or do something else with it. So here's some syntax on a little syntax cheat sheet, but do we have any questions about pointers? These are foundational for what we're talking about today. So if you've even got the slightest question, I do suggest you be brave and ask it, because it'll help us and help me. Or if there's anything online you want to yell out that might be relevant, or if either of you just think of something, just yell it out. Are we feeling good to continue? Yeah? Okay. Here's some syntax, right? So, and again, like I always talk about this, you know, I go on about this. It's a little bit annoying, but in C, we reuse characters or operators. So when we're creating an integer pointer, that's the asterisk means create a pointer to an integer. When we already have a pointer, the asterisk means dereference it. So you have to pay attention where things are used and in what context, because it changes what it does. Okay. Oh, today's dynamic arrays in memory. Okay, it's not too bad. It's not linked lists just yet. Okay. So who remembers us talking about the stack? Does anyone remember it from like early weeks? Maybe you just remember the word. Yeah, a few of you. Good. So when you create a variable in a function, could be main, could be any given function, it's in the stack. Okay? It's called the stack because every time you call a new function, you create a stack frame, which is a chunk of memory big enough to store all the local variables of that stack frame. I might whiteboard this. Should I do it? I might do it on... Should I try Figma again? How did that go last time? Not great. This will do. All right. Don't really want this. Oops. Let's do. Whoop. All right. Okay, here's my really rudimentary whiteboard. Can you all see it? And you can see it online? Looks okay online? Yep, great. So we know our programs start at the main function. The first thing that happens in the main function is we create an integer called age and we assign it 50. So somewhere in here, go away. You know, we get x is stored to 50. In the main stack frame. So right, so a stack frame, there'll actually be probably a few other little bits of memory that get put in each stack frame. Let's just not worry about it. So this is a bit of a simplification. But roughly, this stack frame will be big enough to store a 32-bit integer, because that's how many variables we declare in the main function. Does that make sense? This is the main stack frame within the larger piece of the stack in RAM. When we do something, oh, that should be. That was weird. That was really weird. Anyway, I didn't know you could call those phones. The call's coming from inside the theater. Anyway, age is 50. Whoops, let's not do that. and x is 5 on the do something stack frame. Okay? When this function completes, we kill that stack frame and everything that was there gets destroyed. Right? And if do something, oh, that's a typo there, but if do something calls something else, right, it gets another stack frame popped onto the stack. So it's why it's called the stack, because you're stacking little chunks of memory. Once the function completes, you destroy the stack frame and you come back down to main. In fact, that's how the program keeps track of where to return to once a function is called. It just destroys the stack frame and goes back to the caller. So it's all based on this stack. Why is this? There's a few little nuances here that if you understand this might make a bit more sense. I think it was where you walked in. Do you remember we were talking about static arrays? When we create arrays, so far, we have to know how big they are. Do we all remember that? So we have to give them a size, right? Well, why do we have to give them a size? Why can't we change how big they are? The answer lies actually somewhere here. Does anyone want to take a guess? You can take a guess.
I think I just forgot the guess.
That's okay, that happens.
When you pass it through, it creates a new unnecessary variable.
So the question is, why, given this architecture of stack frames, so variables are on the stack, why does that therefore indicate that we have to have static sized variables, arrays? So arrays have to be contiguous, so they're stored consecutively, agree, but why does that mean we can't change their size? I could store an array here. We do store arrays here, right? Like if they're statically sized. Okay. So I'm going to repeat exactly what you said because it's the correct answer, but so people online can hear me. It's because, like, if you come down and look at the main function, and I ask you, how many variables are in it? 1. And how big is it? 32 bits. 32 bits. Okay. So do you know how big to make the main stack frame? Yeah. Agree. If I have an array up here, and the size is 50, do you know how big to make the do something stack frame?
32 by 50.
Exactly. But now, once the stack frame is created, it's created to roughly the size of the variables inside it. So I can't grow that array because it will not fit in the stack frame. Does that make sense? So basically the answer is, in order to create these stack frames, we need to know how big the things inside it are, which means we can't have arrays that can grow. Because of what you said, arrays have to be contiguously placed. Is that sort of making sense? So it's all because of how this sort of stack stuff works. So the stack is super important. It stores information about how your program's running, the functions that are called and in what order, and the local variables that are created. They're all in each stack frame. And the stack frames, by default, are as small as they can be to store the things that should be in that stack frame. Bree's got an online question.
So someone asked, if you call do something twice, do we make a new stack frame each time? Because it seems expensive to recreate memory on the stack when we can just keep reusing the same frame.
So it's a fantastic question. So if you call do something twice, do we get 2 do something stack frames? Or do we reuse it, or what's going on? So the answer is depends how it's called. Okay, this is kind of bad because this never calls it, but let's call it now. Oh no, why does that do that? Stop doing that. All right. So is this what they mean? I'll give the student a second to check, but let's say I call do something 2 times in main. What will this look like? So I can tell you it won't look like this. Okay, because once a function ends, we destroy that stack frame. Right? So this would never happen. So all that would happen is we do something, then it ends, and then we'd get another one, and then it ends. Okay? But there's still something good to that question, which is like, isn't this a little bit inefficient? Like we have to, allocate that stack frame, deallocate it, allocate it, deallocate it. But in fact, the limitation around why we can't grow our stack frames is the reason for this. And the answer is this stack is pre-allocated once when the program is created. That's why we can't grow stack frames. And it's why it's not expensive. Like we keep saying this, right? Every time you ask the operating system to create memory and assign it to you, that's really costly and expensive, right? But the stack, we're not actually doing that. I can do something 10,000 times. My piece of memory allocated for the stack is statically set. Does this make, so this whole white box on the stack, I ask for it one time when I run the program at the beginning. Doesn't matter now how many times my stack frames get created within it. I'm not actually asking for new memory allocation. Does that make sense? That's why it's fine. Otherwise, could you imagine if every time you called a function you had to request memory? Like our programs would be really, really slow. That's why we can't grow them. That's the limit. That's the trade-off. Okay, so we get fast programs, which is important, but we can't dynamically grow memory on the stack. Making sense? Any questions? I thought that head scratch was a question. I got very excited. Okay, that's good. That's a good motivation. Okay, we've already spoken about this. So whenever you see this, maybe not every time, sometimes when you see this, when you see a block of code, after a function, after an if statement, after a while loop, after a for loop, what you're seeing here is a scoped stack frame. Actually, I don't know if it's true that it's always a stack frame. Crack team of tutors, is that true? Like, is it a stack frame in an if statement? Or is it just a scope within that stack frame? Yeah, so it's not quite true. And when that function is completed, we remove it and delete everything inside it. So we just spoke about that. And we've already spoken about this. So when we create a stack frame, enough memory is there to store everything that the frame will need. All right? The way we know is by something called static analysis. We actually look at the code, we look at how many integers are in it, or we look at the size of the array, and we can see, just like you would see by looking at it, how big that stack frame would need to be. Okay, we got some, okay, well look at this. I don't know why I whiteboarded it. I've got it all here. So here's this one more example. Int user age is 20, a 5-element array. There's my main stack frame. If I now have this function called add two integers together, I pass in some data into the local variables A and B that's popped onto the add to int stack frame, and I've already done the demo in whiteboard. Jesus. Can I unplug it? Does that leave it off the hook? Mute. All right. No questions. You're all confident on what I've just spoken about, yes? Happy? Yeah? Okay, good. All right, so what we're really trying to do here is motivate this problem that we're coming across, right? Programmers are very resourceful. Whenever we have these limitations, limitation being I can't grow memory within the stack, we want solutions. We need solutions, in fact, because dynamic data structures is actually very important. Okay, I don't always know how big my array needs to be. I don't always know how big my linked list needs to be, foreshadowing the future. So what happened? How do I do this? How do I create memory with an undetermined size? A structure that might grow or shrink. If you think about it, what's something that we could do? Well, we could make the arrays big enough to store the maximum length of things that I would need to store in the array, but that would be incredibly inefficient. It would mean my stack frames would need to be huge every time, which would mean my stack needs to be huge, which means my program is horribly inefficient. We don't want to do that. So there has to be another solution. And so the solution is something called the heap. Okay, has anyone heard of it? A couple people? There was some reference here. Oh yeah, okay, it's at the bottom. So in addition to the stack, the operating system will give your program a memory allocation called the heap. Okay? The heap is similar but very different to the stack. Okay, similar, it's just memory that you can put data, right? Just like the stack. Different, that on the stack, only the program puts data on the stack. You actually do not do it, right? You just say, I want an integer called x, okay, and then the operating system, in the program goes off and puts it on the stack. The heap is entirely up to us. What you do with it is entirely up to you. So it sits outside the stack, and unlike the stack, it's entirely managed by the programmer, okay, not the program. Nothing is created there automatically, nothing is destroyed. You have to manage it all. And this is important. This can be really dangerous. This is where people get into problems. And it's what makes C a powerful but difficult programming language. And so having this sort of direct access to the heap is very powerful. We can do amazing things with it, but there's a lot of responsibility here, mostly around the fact that you need to clean up after yourself. So the great thing about the stack is that when this function add two integers is finished, what happens to the frame? It's destroyed, which means all the variables, all the memory allocation, it's all freed. And that happens automatically for you. The function ends and you no longer have access to the data in the function. That does not happen on the heap, which means if you put data on the heap and you don't clean up after yourself, what would happen? It stays there. Not forever, like if you turn the computer off, it's gone. But while your program runs, it stays there. But think about that. Like, so you put something on the heap. It's like a kitchen. It's like if you use dishes and you don't clean them, what happens to your kitchen? It's a total mess. Now imagine that on a device that can do millions and millions of things in a second. How catastrophic it could be if you're not cleaning up after yourself. Right, so I just want to paint that picture. Okay, but it's amazing. The heap is basically infinite space. So it's just as much as you want to use, you can use. So we can do things like have arrays that grow in size, shrink in size, like we can do whatever we want. It's really cool. So how do we use it? C provides us some functions to interact with the heap. This is one of the most important functions. It's an iconic C function called Malloc. It stands for memory allocate or memory allocation. Is that a hand or a scratch? No, scratch. Memory allocation. So you're allocating memory on the heap. Look at this. What does it return? It returns a pointer to the location on the heap that malloc occurred. Because think about it, if you create a local variable called age, you know how to access that data because you have the age variable. But we're not creating variables here. So you need a way to know where that data was placed on the heap. So you get back a memory address because that's how we know where things are. And we decide how large that allocation is. We are not saying create me an integer, which means goes off and does 32 bits. We say how many bits. It's entirely up to us, which is very cool. So how do we do it? So here's not an example, but the syntax for calling malloc. So I'm going to do it this way. Malloc, that's the function call, that's the function name, memory allocation. We give it the size in bytes of the amount of memory we want to be created on the heap. So if I wanted to store an integer here, what would you put here? 4. Bytes. This says byte. 32-bit, correct, but 4 times 8, 32. So you can literally put the literal number 4 there, and you would have enough space to store an integer. Do we do cast types on Malloc, Bree? It's just, we don't do it. But, so let's skip it.
You're allowed to do castings, but I think you're only allowed to cast between ints and doubles. That's okay, and then the rest is just a void.
We just return void pointers. Yeah. Yeah. Must be true. Don't worry, okay, we don't talk about it. Ignore me. And we assign that. Oh my goodness. Does one of you mind calling IT and tell them the phone keeps calling in the... Can I just like unplug it? I ripped it out, don't worry. And we assign back the memory address returned by Malloc to a pointer, because why? Pointers store memory addresses. This is why they're so important. We can also refer to not just to pieces of memory on the stack, but pieces of memory on the heap. All right, so here's an example program. This will Malloc 1,000 bytes. You can do this. It's kind of odd, though, to just put a literal number there. More likely, you do something like this. So most of, I don't know, a large component of the time when we want to put things on the heap, we are still putting a data type, right? Like I need to put an integer on the heap or something like that. So we can use this size of function, which will return back the byte size of the data type that we pass it. So this is great because it's very expressive. So this will store 4 bytes, we'll calculate 4 bytes and pass that to Malloc. So this is basically the most simple invocation of Malloc. This is like saying int x equals 5, or actually it's just saying int x. What if I want to store an array? We could do something like this. We know arrays are just the data type multiplied by the size. So if we want to store an array of characters, we just take the size of a single character and multiply that by the number of elements we want to store in the array. And we get back the chunk of memory big enough to store 50 characters. And we get back, what do we get back from Malloc? The memory address of the first element of that sequence of memory that can store those 50 characters. Any questions on this? Okay, let's whiteboard a little bit more. Should I just whiteboard in person? I think it's probably easier. Did you say blue? Use blue? Okay, hold on. All right, so let's whiteboard this program out a little bit. All right, so we have our main function. Let's not do that. So we have our stack. With the main function on the stack, right? Over here, we have the heap. And the heap is a dotted line. Why? Because we don't really know how big it is. It can be quite large. All right, in this program, we actually have no local variables, but when we call Malloc 1,000 bytes, what we're saying is, jump over to the heap and get me 1,000 bytes of memory allocated, and we return back the address of where that was created. We don't know where it'll be created when we do this. It's just somewhere we get back the address. If I call the size of an int, I'm going to get a smaller piece of memory back. And 50 characters, of course, I'm going to get basically a character array. Typically what you do is something like, let's say you've got int, x, and x is a pointer, equals malloc of size of int. So that's a bit hard to say probably. And so then you've got this x variable which stores the memory address, except that that memory address happens to be on the heap instead of the stack. And everything we do with it is the same. We can dereference it, we can use the address of operator, etc. All right. It's useful to store single pieces of memory on the heap. That's fine. But the really useful thing is to be able to store dynamic arrays. And so this is sort of the crux of what we're getting to. Let's have a look at this program. I'm actually asking the user to tell me how large this array will be. So if I was to look at this program, if you were to look at this program statically, do I know how big this array will be? Do you know how big it'll be? Why not?
We never gave num-elements a number, a value. It's just there. So we don't really know how big our array is.
We don't know what the user will type, right? Yeah, we're all saying the same thing. We don't know what this will be, so we don't know how big the array will be. If we don't know how big the array will be, how big do you make the stack frame? Well, the program can't know and can't do it. So let's do it on the heap instead, which is what this program is doing. So here I'm storing how many elements I want the array to have, and I scan it in from the user. So the user could type 5, they could type 5,000, we don't know. And then here's like the important line. And if you can get your head around this, you're in a good spot, I would say. So let's break it down. I call malloc, right? At the end of the day, it's a malloc call. Malloc always needs what to be passed to it? The number of bytes. Always, at the end of the day, that's what you're giving malloc. You're giving malloc the size. This is just a way to calculate size. So at this point, the user has typed in a number. Let's say they've typed in 5. It's going to be the number 5 multiplied by the size of, in bytes, required to store an integer on this platform. So let's call that 4 bytes. So here we'll get back 20 bytes. So malloc gets passed 20. It goes off on the heap and creates enough memory to store 20 bytes and returns back the pointer to data. So data is a pointer, an integer pointer in this case. And then the program ends. And what this means is that data is an integer array as well. Let's run this program and see how this is working. Let's go SSH. Yep, doesn't like that apparently. All right. We can just copy this, I think. Do I need standard lib? Is that right, guys? Yeah. Yeah. So Malloc lives in standard lib.h, which I think we introduced last lecture. So, all right, let's have a look at this program. Let's just check that this compiles. I run DCC to dynamic arrays, output to a program called program. Make sure there's no error there. That's fine. Oh, yeah, thank you. Here. Scanf int, yeah, thank you. Oops. What? Go away. All right, and this is just saying we're not using data yet, so that's fine. Okay, so the program runs. If I run the program, there shouldn't be an error, and the program should just end. Oh, it's waiting for me to scan, of course. I type in 5 and then it ends. How do I prove to you guys that this is an integer array? So let's just do array things with it. So while int I is equal to 0, while I is less than, let's just say, num elements, printf, or let's just go, actually, data of I is equal to I. Right? This is familiar from arrays, everyone? You're all exhausted from the assignment, aren't you? And here, let's just go printf, %d, \n, data of I. So we can all agree, right, that I should say I equals 0. Thank you. Okay, we agree that these are just, array things that we can do, right? We use the array name, we use the index to access the element, etc. Let's compile the program. We shouldn't get a warning now because we're doing something with data. We run the program. Let's say I enter 5, and then we go 0, 1, 2, 3, 4. So we looped through the array, added data to each element, looped through again and printed each element out, and you can see this data variable is working exactly like an array, except it's on the heap. Which is really cool. Who thinks this is cool? Is this cool? No, not cool. Cool-ish, cool-esque. Yeah, okay, cool. All right. So you might be saying, okay, Jake, yeah, you think that's cool, but this isn't dynamic, right? It's just set to 5. How would we make this dynamic? Do you have a question or a statement?
My question is, if you don't give your array any values, do you still have to free it?
Ooh, good question. So do you mean here?
Let's say, you don't set any values in your array, do you still have to free it?
Okay, the question is, if I don't assign any data or any values to the array, do I need to free this memory? So let's take it to the audience, right? What do you think? Put your hand up if you think you would need to free it?
You can just leave it there, right?
Put your hand up if you think you don't need to free it.
Good if you did.
Say? What do you say?
Good if you did free it, but
So let's take the assumption that we should be good programmers and free after a memory allocation on the heap. Assuming that we should, do we have to if we don't do this? So who thinks we have to? Now, oh, you've changed your mind, or you always thought that? Or you don't know. And who thinks we don't have to? Why do you think we don't have to?
Because we haven't initialized it in the first place.
Okay, we haven't initialized it. We haven't put data into it. But did we request the operating system partition the memory for us?
Yes.
So does the memory exist?
Yes.
So should we clean up after ourselves? It's like saying I didn't serve the food I cooked in my kitchen, therefore do I need to clean the dishes? You still used the dishes, or you still took them out of the cupboard. You still asked the operating system for 5 times 4. It exists, right? And now you're saying, oh, but I never used it, it's not my fault. Well, you did. You asked, it doesn't matter what you do with it. Right? You ask the operating system for the memory on line 9, here. So you do have to free this.
So it's like you take empty plates out of the cupboard and put them back.
Yeah, it's like taking empty plates out of the cup and putting them back. Yeah, I suppose that's a reasonable thing to say. Like, the operating system still cares that it lost its plates. And it still means that other chefs in your kitchen can't use those plates. So yeah, you didn't clean them, you don't have to clean them, they're clean, but you still took them. You took the resource. And it's the resource that's limited. Yeah. That's a good question though. Any other questions like that? More like that, please. Good question. Basically, if you see a malloc, here's a super quick way. In fact, there are real analysis tools that work this way. Anytime you see the word malloc, you need to free. In fact, it's anytime you run malloc, you need to free. But if you see malloc, you should see a matching free.
Someone online will ask, how come because you don't free, you allocate data? How come it still compiles /bonus?
So I'm not freeing malloc, and I'm not freeing anything yet in this program. In this particular case, not freeing is not really a problem because there's only one function, and as soon as main ends, the program ends. So I should clarify, because some people get confused about this. When the program ends, the memory is all freed by the operating system. So it's not like it's going to exist after the program ends. It's a problem for longer running programs. So imagine you've got, like assignment 1, for example, you've got a game or something, a program that runs in loops and does lots of different things. If memory is getting created and not freed, then the longer the program runs, the more memory you're consuming. That's called a memory leak. Have we heard that term before? So memory leaks can cause programs to crash, and it's because they're mallocing memory and not freeing it. And when it only surfaces if the program is long running. So to build good habits, we need to free no matter what. So really all we should be doing here is saying free data.
Can we talk about leacher?
Yeah, let me do a few more slides and then let's talk about it, but do remind me. Okay. So this is all you need to do. You pass it the pointer to the memory allocation on the heap, and you pass it to this function called free, and free will go off and destroy it. Or not really destroy it, actually, just mark it as available, but whatever, same thing.
Can you free a specific data point? Like say data has like 5 things, right? Can you just free like one of them?
So in this case, you're saying that because data is an array, could I free one of them?
Yes.
The answer is yes and no, actually. Could you free something in the middle of it? No, because arrays have to be contiguous. So then you'd be destroying the array. Could you do it? I think so. You can kind of do anything. But then you're in hell, because then you've got data that's allocated to you without a reference to it, without a pointer to it, the second part. and that would be nasty. You'd actually be incapable of freeing it. That's such a bad memory leak that you're in real trouble. So don't do stuff like that, but you can actually do it. Sometimes though you do, it is valuable sometimes if you've got an array here, you want to just free that part. Free off the end is useful. Sort of. No, it is, yes. Oh, yeah. We got more slides.
Can you free memory when you pass it into the heap?
You can't free memory on the stack. Is that your question? Yeah. That doesn't make sense. The stack memory is managed by the program. So when that function ends, the stack is destroyed, that's the free.
Is there something you can put inside that will delete everything in the heap?
Ooh, is there a function you can call that frees everything on the heap?
Because let's say you have a game and you finish the game, you just want to free everything.
I don't think there is. There could be, actually. I don't think there is. But if the game ends, you just quit the game and the memory's freed.
I mean, after you do the main, you're going to need to have free this, free this, free this, free this, free all that. You can just have free one thing and then everything else is deleted.
You probably should do that. But even then, that's not really what we care about. I've just done this here as an example. When we free is when we're finished with the data, not when the program... If we're only freeing when the program ends, we're not doing anything to clean up after ourselves because the memory will still inflate. What I mean by this is like if I've got a function like, void do something on heap, and I have a malloc here, whatever, what I'm saying is I should free when I'm done with it, during the program. Basically, like going back to our kitchen analogy, it's if I take some plates out and I finish cooking, one component of my meal, and I'm finished with that, right? This happens, we all cook, right? And you okay, fry some onions, and then you're finished frying the onions. What I'm saying is you should clean the pan and put the pan away, and then continue on cooking. If you wait until you've finished all your meals, all your cooking, and then you've got 50 dirty pans, that's still a nightmare. Do you know what I'm saying?
Yeah, but like in this case, you cannot have infinite plates. Can you just do it like have different names, and if you have the same name for two mallocs, you can just...
We don't really have infinite plates. Like RAM is still limited.
Practically,
But RAM is still limited. It's still a limited resource. So we want to free the memory as soon as we're done with it and we know we won't need it again. Does that make sense?
But like, could you just keep everything, just have different names for everything, and then once you finish the program, everything finishes? Because what if in case you need it sometime later? As long as you have different names for everything and it's organized and structured, you don't have to delete them. Because you have practically like so much plates, you don't need to keep cleaning every time.
I don't get the question. Did anyone else catch it? Do you want to repeat it one more time to the tutors? Or repeat it one more time to me and I'll try.
Okay, in this case here,
Here, this program.
like in general,
Yeah.
you will have to delete the data after you finish using it.
I have to delete data after I finish using it, correct.
How about you just leave the data there, keep like having different names for every other malloc that you use, and you can have so much things in the heap and they don't have to get deleted. You can just reuse them in case you need them later on.
So what you're saying is, if I need a different array, just make a different reference, which is fine. But I think the part you're missing is that let's have a function here called do something on heap, and do something on heap needs to call malloc, and I call this function, let's say 1,000,000 times. If I don't free, how much data will I have created? How much? You can tell you 1,000,000 times 5 times 4. Okay. But once the function ends, I don't need it anymore. So if I freed, how much more efficient? 1,000,000 times more efficient. Do you understand? Because you've got to think about things as we're doing them in programs that can run millions of times a second. So there's things you need to do that needs to do a malloc. And so you've got to think about it as not as this is a few plates in a kitchen, but this is a supercomputer that can do millions and millions of things. So you need to free as soon as you think you're finished with that data. Did you have a question? Didn't you? Did someone put their hand up? I thought you, I swear you did. Anyway, okay, I believe you. Did that answer your question? Okay, good. Any more questions? All right, what have I got here? Okay, freeing malloc data, and then we'll have a quick break. So this is our responsibility. A little bit, you got to trust me when I say you should be freeing after yourself. And you'll learn when you write a program that has a memory leak. Memory isn't infinite, even though it feels like it. You will crash your program if you use too much memory, or it'll slow down that it's not usable. If you're writing programs, for example, iOS apps, okay, we're thinking about computers a lot here, but iOS apps, Android apps, they're mobile devices, limited battery, limited RAM. What's an iPhone? Got like 8 gigs still? Which is still kind of a lot, but imagine if imagine if the apps on your iPhone didn't free, because think about, iPhone apps is a good example for why this is important actually. Do iPhone apps really end?
No.
Do you really end an iPhone app? No, never. They run forever. You just resume them when you switch apps. And ideally, you go back exactly where you were. So if your iOS apps kept mallocing memory and didn't free them, iOS would kill the app. That's what, sometimes if you've ever seen an app crash, it's likely that something like that happened. So you really don't want memory leaks. It's really bad. So we need to free our data. So basically, you saw this, but anytime you malloc data, we need to free it. And you want to free it as soon as you know you're done with that data. There's no rule to exactly where that should be. And you don't want to be too premature when you free data, because if you free it and you need it again, you need to remalloc, and every time you ask the operating system for memory, that's inefficient. So it's a bit of an art to know where you should free. I'll end this segment with what Bree wanted to talk about, which is that there are some tools to help you to know if the program that you've written has a memory leak. So Bree, you're going to have to help me out here. So let's say I've got this program that doesn't free data. Like that? Oh, at the beginning, yeah. Then I compile it like normal. Whoops. Dynamic array. Out to program. Or I don't out it? No, I do out it. Okay. So let's have a look. Do you all see this? Sometimes it gets cut off. So if I pass the leak check flag to DCC, this will actually run some tools to detect if the program you wrote mallocs data without freeing it. Now in this case, I removed that free line. So I'm hoping, you then run the program, I'm hoping that it will detect it as a memory leak, but it may not because, I got to put in the number, 5. There we go. So I just had to enter the scanf here. The program runs like normal, and then I get this error. Free was not called for memory allocated with malloc in the function main in the file dynamic array.c at line 16. So there are tools that we've built into DCC that do leak check detection. Memory leak detection is there's lots and lots of different tools that exist out there that help you to detect it, because writing programs that have memory leaks is pretty catastrophic. Right? If your iOS app crashes every 30 minutes because you've got a small memory leak somewhere, no one will want to use your app. And your Facebook company worth $1 trillion will be worth nothing. It's really that critical. So you really don't want leak checks, and if you can detect them, there are tools that help you, and DCC has a really good tool in it to do that. In fact, I think with assignment 2, we run leak check on your auto marking. Is that right? We run leak check on when we mark your, not labs, but stage 3 of assignment 2. So you cannot write memory leaks in assignment 2. We will deduct marks for you if you do.
For this one, it shouldn't matter because the heap is destroyed.
Yeah. Okay. So you're saying that the program's ending anyway. Why do we care?
Yeah.
Habits.
So
It's habits. Habits is why we care. This is still technically a leak check. When the program ended, or in the life cycle of the program, you malloc data and you didn't free it. It's technically still a memory leak.
okay, so it's good habit.
I agree, it doesn't eventuate as a problem in this case. But let's get into good habits from the beginning, and you won't get your first job as a software engineer, and you'll be writing memory leakable code.
So say in assignment 2, right? You have
This would still fail marks.
okay,
Yep.
5 thing, you just write 5 frees at the end.
Yep.
Okay.
If you've got a malloc, you should have a free. The tool doesn't care, by the way. So the tool doesn't care whether or not it's a cute little memory leak or a catastrophic one. It just knows that there's a memory leak.
What's a memory leak in the kitchen?
A memory leak in the kitchen, in our analogy, is when we're taking pots and pans out of the cupboards. So we're acquiring the resource, and we're using them, and then we're finished with them, and then we're not putting them back. So it is kind of a useful analogy here because it's a limited resource. Okay, let's have a break. Go grab a coffee, go to the bathroom. We'll come back, Kahoot, and we'll actually finish off the malloc content into what makes us have really dynamic arrays. Okay?
I'm just here to help answer questions.
Oh, thank you. Yeah. I get the Kahoot up, actually.
Do you have the cards ready? Oh, yes. Very quiet chat, but there's 2 people who ask a lot of questions.
Are they good ones?
Some of them, the ones I've been asking, yeah, but not a lot of them are just kind of extension thoughts.
Right.
We
Yeah,
can't
that's
too
okay.
much. So it's okay. But some of them are good questions.
Good. Does anyone have questions for Bree or myself?
That student was asking about duplicate calls to functional stacks. Like he was asking why what came to my head, was he asking about recursion?
I don't think he was. I thought about that too. I think he was just saying I answered it taking it as why destroy the stack frame if you might call the function again? Because we talk about all the time that every time you create memory that's costly, but I did try to clarify. Yeah, I could have gone either way, I suppose. Yeah. It might have been a good time to introduce recursion, but I don't actually think I've got a Kahoot.
There's no such thing as a good time to introduce recursion.
Yeah, I agree.
Someone's asked in chat if we can do an example of malloc a stream.
Yeah, I got time for a demo at the end. So
That is what someone's asked for a demo.
yeah. So maybe when I get to the demo spot, remind me to do strings.
Yes, if we have time.
What do? You just malloc the character array and then put the null terminating character in the last spot?
I guess.
Oh no, you just assigned it a string. Yeah.
But they want to.
Yeah, okay.
And they can I guess you can have you have 2 strings and then you reallocate the memory for the second string to be the first one. Like your dodgy version
I think you just malloc the character array and then a string copy into it, right? That's what we do.
Yeah, sure. That sounds like I'm not really sure what they mean. I think they just want to see Malloc with different types
Yeah,
of
okay,
arrays,
yeah.
like just a char array. I don't think it's specifically, like we wouldn't really use Malloc for strings anyway, so I'm just like, cool.
Yeah, that's right.
It's because we don't, I think it's like this week is really weird because it's like we try to hint at linked lists. But
Yeah,
there's like
it's
so many
setting us
random
up for
things.
linked lists,
Yeah.
exactly. I don't think I've got a Kahoot. What should we do?
No Kahoot. That's not possible.
It's not there week 8. There's no. Maybe we missed a.
We're week 7.
Oh my god, we're week 7. Thank you. Thank you.
Well, you'll be still here tomorrow, right?
Yeah.
You're gonna go for a Sunday too.
I don't think we'll release it tomorrow.
Oh, but oh yeah, okay.
Thursday probably. Give them a couple of days.
Oh yeah, I don't think it's even that bad if we release it week 8 because most of them don't even like we haven't
Yeah.
really done enough of this anyway by the time it gets end of week 7.
Yeah, that's right. We'll see. Yeah, we'll see how we go. It doesn't hurt to release it a bit early anyway for people that want to.
Alright, you're live.
Thank you. I hope you're participating, Henry, in the Kahoot.
Oh, I will.
We had a couple like a year ago. I don't know if you guys were around, but remember before you were streaming the lectures, we had like a guy from the faculty. He was like not a computer science student. He was just some guy from the faculty. He streamed for like a year, like 3 terms in a row, and then one time he won the Kahoot. it was amazing. It was so good.
But did he go in every Kahoot?
He might have. I don't know. But one time he's like, "Oh, I won." It was so good. Yeah. All right. Shall we start? 40 students. I'll give it a few minutes. All right, ready to go? A Kahoot by Kahoot, interesting. All right, 8 questions. If you have a variable int a, how would you get the address of it? Oh, I like the oh shit. All right, very good. Ampersand is address of, asterisk is dereference. Let's power through. Question 2. How many stack frames do we have when the code is executing at line 6? Don't listen to them. Very good, it is red. When we're at line 6, in that position, before we call the foo function, we've only launched the main stack frame. So we have one, right? If we were inside of the foo function, we would have two stack frames, main and foo. When foo ends, we go back to the one, or whatever it is. Okay, how many stack frames do we have when the code is executing at line 12 now? So remember, it's called the stack because we stack on top every time we call a function. When the function ends, we pop off and go back down one below. How are you seated? That's nuts. It's fine, you can stay. It's just weird. Yeah, logically it's true, correct. Good. You all got that, that's really good. Yeah, well, otherwise we take too long. How many stack frames do we have when the code is executing at line 22 now? So you get the idea. Bree, careful. Very good. Why is it 4? We have the main stack frame, main calls foo, we have 2, foo calls bar, we got 3, bar calls baz, we have 4. All right, we can see the podium now. Who's creative bat? I hope it's not Henry. It's you. Sturdy Gecko? Someone online? Lucky Bunny? You, okay. 2 in the room, but one's a tutor, so come on, fix that. How many stack frames do we have when the code is executing line 14? I mean, we were sick of this question, but. Yeah, 2. Why is it 2? Oh, most people put 3. Why'd you put 3? Who put 3 and wants to explain their thinking? Who put 3? You did? Why? Yeah, so because bar has finished, its stack frame is destroyed. So we're just left in the foo stack frame, which was the second stack frame created. So we created main, and then we created main called foo. We're still in foo, so we've got the 2. We created bar and baz, but they were both destroyed, and so we've got 2 left. Oh no, we still got a tutor on top, so, but we've changed the rest of the podium. All right, 3 more questions. What is the correct way to malloc 5 integers? So were you paying attention? I guess this Kahoot was done during Halloween last year. Okay, that was apparently an easy question. Probably not much of a change, just from speed. All right, second last question. What issue does the following program have? Yeah, that's true. It prints the number 5, Brie. That's very useful. Very good. This program technically has a memory leak. We mallocked data, we didn't free it. We've been talking about that. It also doesn't do anything useful. So if you said that, you got the mark. The one person. Okay, last question. Hopefully it's difficult. If free isn't called, does memory allocated with malloc ever get released? Okay, so apparently red's also correct, but yeah, heap memory will be freed when the program ends. The operating system wouldn't let programs leak memory outside of the program's execution. That would be so catastrophic your computer would probably shut down or stop working. I don't know why red was also acceptable, to be honest. It would get released when the program ends. Anyway, I guess both are okay. All right. Let's see. Do we have a last minute change? Creative Bat? Who was that? That was you. Who was it? It was you. Yeah. Cheerful Camel? What does it say? Nice job. Charming Sloth? Who are you? Henry? No. It wasn't Henry. Someone online? Okay, well, I don't know. Do we give Liam a card? I guess so. Yeah, you can go first. And then give that to Liam in the blue shirt. You have to. It's the rules. I don't make the rules. And then if you won online, you just give me your... Yeah, show the camera. You give me the podium screenshot next week. Actually, give it to Henry. Henry's taking the lecture next Monday. All right. Okay. Did we learn? Hopefully the Kahoots, they're a bit of fun, but I find that they do actually clarify a few small misconceptions. So it's always good to get some practice. All right. One more opportunity for all of you. Please have a think about it. Do you have any questions on malloc and free or free? We're feeling okay so far? Good. All right, something else that I want to introduce is the realloc function. Let's call it the slightly more sophisticated cousin of malloc. It stands for reallocate memory. Okay? And it can do a few different things depending on how it's used. Okay? It either resizes an existing malloc allocation, so memory allocation on the heap. So, it takes an existing memory allocation via a pointer. If the size of the reallocation is larger than what the original malloc memory was, it grows that memory allocation. So this is how we have dynamic arrays, truly dynamic arrays. So it can grow up a memory allocation. But sometimes we pass a memory allocation to realloc and we want to reallocate less memory to that allocation. Realloc can also handle that case, and it's exactly what you were asking about earlier, and it's the reason why we don't typically free data at the end of an array. We just realloc. Because realloc will free the tail, right, the unnecessary data at the end of an array if we're reallocating to a smaller amount of memory. Okay, so I know there's a few things to that, but we'll take a look at an example. It's not too complex. And it always returns the address of the new allocation, even if it's in the same position. So this is kind of getting to something kind of interesting and important that we don't really need to worry about. Maybe it's more of a 1521 thing, but when we reallocate memory, either if we shrink memory or grow it, sometimes the operating system will decide that it's beneficial to the operating system to move that allocation. So realloc is not in place. So what that means is, so if I've got some memory here, data, and it's got 4 elements, 0, 1, 2, 3. Okay, so data is a pointer on the heap somewhere with some Malloc data. Does that need to, yeah. And then I pass data to realloc, and now I say I want the size of an int times 6, right? So I'm growing by 2 because I could only store 4. It may just literally expand it if there happened to be room here, at which point you would get back the very same memory address. That may happen. What else might happen is that something was here and it can't put it there. So what would it need to do? What would you need to do? Move, and not just, you're not just moving this, what are you moving? All of it. So maybe there's room here. And so this gets returned. So realloc, just like Malloc, maybe even worse, you really don't want to call it if you don't have to. Because look, all I wanted to do was grow my array by 2 elements, and now I had to allocate 6 elements. Now, these are small numbers, but imagine there's 1 million elements here. I want to grow it by 2 elements, and now I've got to, all of a sudden I have to make an allocation of 1,000,002 elements. That's really costly. So be careful. Not be careful, don't worry about it for now. Like, this is more of a 1521 problem. How to optimize this stuff, but it's good to be aware of. Does it only change positions of it if it's growing? So logically, if we're reallocating to a smaller number, let's say this is a 2, what realloc does is free this piece of memory. Okay? So this gets freed. So logically, we know this could always happen in place. Does it always happen in place in reality? I actually don't think the answer is yes.
It might reshuffle it.
Yeah, it might decide, okay, let's imagine you've got this really memory constrained puzzle, and there's data here, there's data here, this is free, there's data here, there's data here, and then this is all free. And let's say there was data here, and this, actually let's change it. Let's say there's data here and this was free. And then the user reallocs this. The operating system might say, well, why don't we put it here? And then I get all of this available for something big. So it may actually shuffle it around to optimize. Yeah. Because it's good to have large chunks of memory free for large memory allocations. The problem, this is why requesting memory is always so costly, because if something came and wanted to malloc this, right, your operating system would have to reshuffle all this stuff. To add complexity to this again, which I probably shouldn't do, memory addresses don't change if the operating system is moving stuff around for you, but the layer between physical RAM and the OS can actually shift. don't worry about it. There's a layer of abstraction between pointers and the memory that you interact with and physical memory. So it can optimize things at another level again. Anyway. So that's realloc. How do we call it? What's the syntax? It's just like Malloc, but but you also have to pass the original memory allocation, obviously. So just to remind you, I'll copy this into VS Code just so it looks a bit nicer. I should probably copy. All right. So can you all see this? So I've got 5 elements stored in this integer here. I malloc the 5 elements. I add 40 elements. So my new array size will be 45 elements long, right? So I need to reallocate data. And this is the syntax for it. It's pretty simple. So you just say data, you reassign data to the resulting address of calling realloc on data. So we're reallocating the pointer at data, yeah? And then just how big should it be? It's a great function because it just handles that complexity for you. So if the 45 is greater than 5, it would grow it, maybe move it. If it was less, it will free the rest and maybe move it. That's why you must not forget to reassign data. Technically, if the realloc happened in place and it didn't need to move it, it would work, but you can't guarantee what realloc will do. So this simple addition, the realloc function, gives us probably the most important component of a dynamic array. We don't need any more tools. We can now create dynamic arrays. So if we have an array of 5 elements and all of a sudden we decide we need to store 15, well, what do? What would you do? You just realloc with adding 10. And then all of a sudden, that very same array with the 5 elements will now have 15 elements. Do we have any questions? Is it clear? You're all wrecked from the assignment, yeah? Does anyone, please, if you can think of a question, even though you might not really need to ask it. It is nice to get asked questions, but okay. Yeah, we've spoken about this all lecture, but pointers to a data type in the heap can act as arrays of that data type, right? We've been doing that all lecture. So pointers decay to, or arrays decay to pointers, whatever. Okay. Cheaters, is there anything I should add so far? Should we just get into a demo with reallocating? Should we do something with strings? Oh, maybe we'll do a really simple integer one first, and then we'll do something with strings. So dynamic arrays.c. Okay. So let's do this in the way that we should be doing things, which is in a function. So I'm going to have okay. So here's what I've got. I've got a function that returns a pointer to an integer. Do we do it like that? Now I can't even remember. That's going to store some array of integers on the heap. Okay? So that'll just create it initially. Then I'm going to have a function that will add a single element to that array, which means it'll need to reallocate every time. Maybe, actually. We'll see what we get up to. And we'll handle this all in main. So create data is going to create the initial malloc on the heap for an int array. So can you guys just tell me what to type here? How would my create data function create a memory allocation on the heap for an integer array? But let's just say there's a single element in it. Make a variable. I could make a variable. I don't actually need to. Malloc size of int. That's right. And then what with it? Yeah. So I can actually just so malloc size of an integer and return that straight away. God. I know, it's very intense programming. So this will return back the memory address on the heap of a allocation of memory large enough to store a single integer. Okay? Which is technically an array of one element, by the way. So that's what we're banking on. So what we will do in main is we need to store a reference to that data array. So we'll say int data is equal to, and what function do I call? Create data. So data stores the address on the heap of the array. Well, let's call it array in quotes because it is just an array of one element at the moment. All right. Now I want to finish this add data function, which should expand the array by one element every single time I call it. So what would we do here? There's also something missing, by the way, in the parameters to this function. I need the star on the x. Yes and no. I need two things. What do I need? You don't know? Yeah, I need the array and I need x. So you were sort of right. I need both. I need that. So I need to know where was that array on the heap to grow. Like I need the reference to the array in this function, and I need the element that I want to add to the increased array. Yeah? Yes? What's one? This isn't how much I want to grow it. It's the new value to add to the array. We can whiteboard it in a second. So I've got data, which is my array on the heap. I've got x, the new value. We can call it value to add, by the way. Maybe that's more clear. So what do I do to data here? I have to reallocate it. So what do I type? Yeah, we can start there. Realloc. Then what? Yep. Then what? Not value to add. Value to add is the value I want to add to the end of the array. So if I put, let's say I wanted to add the number 10, that would expand it by 10 elements. That's not what I want to do. I always want to expand it by how many elements? by 1. Sorry? But if I give it 1 here, it'll always set it to 1. So I need to say whatever the current size is, but 1 larger.
Yeah, so the size of the data
Plus 1. Plus 1. But hold on, Bree, John, can I do size of data? Yeah, I don't need to keep track of.
You can take a variable or a type.
But does it get the length automatically?
Give you the size of an input pointer.
Sorry?
If you do size of data, you'll get the size of an input pointer.
So I need to manually keep track of the size. Yeah, so we're actually missing some information here to do this job, right? Okay, let me clear this whiteboard very badly. So when I create it, I always get back a single element with an integer. In my add data function, what I want to do is take that allocation, whatever the size of it, I want to say the current size plus 1 to the realloc. Right? We're just growing it by 1. So it means I need to keep track of how large it currently is. And C doesn't do that for us. We actually need to do it. So in main, I need to keep track of this. When I call create data, what's the size of it?
1.
Yeah, 1. That's right. So when I call add data, I'll need to give it the current size and the value to add. I can give it data, the array size, and the value to add. For now, we can just say 5, but we'll make it a scanf, I think. Okay, so armed with now the new information of the current size, what do I pass to realloc? Maybe you can finish off what you were saying before. Let me start fresh. Size of, so let's do size of what first? What's the, no, size of you pass a data type. So this is how we know, so let's look over to the, I don't know if you can see the whiteboard. There's a single integer in it. And what I want to do now is make it 2, I want to grow it by 1. So data is just the memory address of the start of the array. So data plus plus won't work.
You do the current size plus the value to add and you times it by the size of the integer.
We don't care. We're reallocating here, guys. We don't care what data we're adding. We just need to know the size of the grown array. What's the current size of it?
The current size.
Let's say in this program, when we're calling it here for the first time, what's the current size? 1. What should the new size be? 2. The current size is 1 multiplied by the size of an integer. What? Yeah, int. What should the new size be? 2 multiplied the size of an integer. So how do we calculate that? The current size plus? No! Plus 1. The current size, which was 1, plus 1, times the size of a what? Say it? An integer.
So we need to give the value to add.
No. We're just asking for the allocation. We haven't added the data yet. I need to grow the size of the array, malloc the data, or realloc it, and now I can say data of.
Oh, this is what you, okay, good. I was thought you were doing something else.
Well, I also forgot something on the realloc line. What did I forget here? Not free. Yeah, sorry? Yeah, I need to reassign it, yeah. This should actually be probably an int that returns the current size. Or maybe we don't do that, actually. Okay, I feel like there's confusion here. Who does this make sense to? Okay, does this not make sense to anyone? Okay, yeah, you're nodding emphatically. I hope that's legitimate. Is anyone confused by this line? So we're not quite finished with this function. We've grown the array, but we've not done anything with value to add, which I feel like is what was throwing all of you, maybe. We just need to know how much memory to reserve, which was whatever it used to be, the current size, plus 1. So it used to be 1 element, now it's 2, times by the size of an integer. So it's literally like I came to you and I said, I need you to reserve. So I used to have 1 seat reserved in this row. I now need you to reserve 1 seat plus 1. 1 plus 1 seats. So how many seats would you reserve? The one next to you. Yeah. Okay, now I've grown it and I've reserved it. What do I have to do with the value to add? What? Sorry?
Current size, you have to say current size plus 1.
Let's not worry about current size just now.
Add the value to add to the block, the newly created.
Yeah, so we just expanded the array, right? How do I put value to add in the last element?
Do the current size plus.
Tell me what to type. I can use array notation.
Start of square bracket.
Yeah?
And then current size plus 1.
Careful.
Oh, you need.
Careful. Someone help him. Why can't I pass current size plus 1? I have to start from 0. So what do I type? Yeah, current size. Then what do I do? Equals what? Yes, thank you. That's it. People are still following? A little bit? I don't know, you guys are... Could we have done it here? Could we have done what, sorry? Ah, good question. That's actually a very good question. So this student asked, here, instead of doing current size plus 1, could we have done current size plus plus? The answer is actually no. Can anyone say why the answer is no? It wouldn't actually work. Why would that not work? No, it's fine. Current size plus plus, what does it do? Your thinking was right. It adds 1 to current size. Why would this not work? Ah, that's right. It adds it after it's used. So actually what this would do is read current size, pass that to realloc, and then add 1. But there is a way to solve it. You put it before. That's a what's the term for it? Pre-increment?
I thought would absolutely put the like before that.
Oh, you didn't even mean this. Oh, all right. Oh, well. This is legitimate syntax. So this means add 1 to it and then read it. Yeah. But then we actually have to do this. Sorry? I can't hear you. No, that gives you, that adds it. I thought this adds it, then gives it to you. I'm pretty sure. But the problem here is that this is kind of pointless because this doesn't return current size. But it probably actually is a good thing that it does. So we could do that. I don't know. I'm a bit conflicted here because now you've added 1 to it. So now it would be 2 elements. So the index would be 0, 1, 2. That would be the third element, which is an error. So we need to go back 1. So this is fine. Then we just need to say that array size is equal to, was it add data? Yeah. Was I right or was I wrong? I think I'm right, but let's find out, I guess. Okay, shall we check if this works? Oh, there's another problem with this, by the way. There's another problem with this program. Yeah, I should do that, but that's not the big problem. This will crash. Anyone spot it? Come on, I'll give you a Pokemon card if you spot it.
Do you need to put the star on the data?
No, that's fine. Come on. I haven't freed it, but that's not what I'm thinking. There's a bigger problem. Free won't cause it to crash. Like I'll add here. I'll do a void print. I should do this first. Print. Hold on. Come on, someone's got to spot it. It's not too difficult.
Well, you didn't assign anything to the first one?
Yeah. There's no element for the first when I create data. Whoa, what has that done? I didn't put anything in it. So I could just do that here. Okay, let's see if this actually works. There's a few things that could be wrong with it, so let's. I've got to add.
Can we see like an example where the program crashes?
Yeah, we can just not do this. I don't think it'll spot the error. Yep. And there's the crash. Because it was trying to read this might be a different problem. But let's see. I might have a different bug here, by the way, so let's make sure this actually works. But let's compile this with. Okay, I do have a problem. Attempt to free memory that's already been freed. Okay, there's something wrong with realloc, indeed. Array size here, add data, array size. Oh, array size should be, 1. Add data gets array size. Array size is currently 0. Sorry, it's currently 1. I make it, am I wrong?
You're reallocating, but you're not returning a pointer to the heap.
That should be, is that the problem? Current size is 3. Value to add is 5. Well, let's see what DCC help says. Maybe it'll save us. Got too much writing here. Yeah, I think I do need to return the address of it. But that's a copy. Yeah, I would need to, so let's not do that. So let's do int data. Sorry, int, whoops, not there. Let's do that there. Return data. Let's not do this. Okay, we return data. Here we need to say data is equal to that, and then array size plus plus. I think that's the problem. I hope that's the problem. Agreed? Okay, great. I can explain what happened there, but let's just check how this is working. So we initialize the data here with create data. We set the first element to be 1 because we had a single spot for it. And we're manually setting the array size to be 1. Okay. We call add data. We give it the array on the heap, the current size of it, and the data that we want to add. In this case, it's just 5. I can make this like 6 and 7. Maybe that's a bit clearer. When I call add data, which accepts that array, the current size, and the value I'm wanting to add, we reallocate based off the current size, but 1 larger, multiplied by the data type that we're storing, the size of that, and we store that back in the data pointer. The problem before was that I wasn't returning this new data pointer, and it's exactly what we were talking about before. Realloc was shifting around where that array was going, but I wasn't returning back the new location, which was the problem. There was another solution to that problem, but this is better for us. And I'm actually placing that new value to add in the last element of the array after I grow it. So that's that initial value. We've grown it 3 times, adding 5, then 6, then 7. 5, then 6, then 7, and then I'm just printing it at the end. Okay, so we didn't get to our character array demo, but this was, I think, a pretty good demo. Of course, the live code is all synced for you, so if you want to go back and look at this, if you want to really get a good understanding of how this is working, I really suggest you whiteboard it. So draw your memory allocation on the heap for the initial allocation, run through the program line by line, and grow the array as you do it, and you'll see what the program's actually doing, especially if you return back the reference to the data point on the heap. Okay, I'll see you tomorrow for a streamed lecture. Good luck with finishing assignment 1 and submitting that this afternoon or this evening. We'll give you a couple days, not much, but a bit of a break before we release assignment 2. So get some good sleep, and I'll see you tomorrow. Thank you. Oh, I didn't do feedback, but whatever. Oh, thank you. That's yours.
I came second
Today? Oh, last week. Second, so you get to pick from 2. You gotta show me. Oh, that's a good one. Yeah, that is a good one.